Hi everyone. So as always we start with the learning objectives, and you'll see that most of these things you've done in the IGCSE. So we've talked about the forces between charges, we've talked about electric fields, we've talked about current. However, we're going to go much deeper here. So all these things that in the IGCSE I told you, oh, this is very complicated, we're not going to calculate it and so on. Well, now we're going to calculate it, and some of it is complicated, but it's doable. So let's get started. So before we start, I would like to go over some things that you should already know from the IGCSE. Things like there's positive charges, there's negative charges, they attract, positive charges and positive charges repel, negative charges and negative charges repel. Now there's two types of materials, remember? There's conductors, and in conductors, charges, in particular electrons, are allowed to move freely, and then there's insulators, where electrons are stuck, so they can't move. And because they can't move, they do not conduct electricity. Now, I don't know if you've ever wondered how we know that it's electrons that carry electricity in wires and not protons. And because it turns out that you can't just look and see whether it's an electron or it's a proton. Electrons are tiny. They're tinier than atoms, and remember, there's 10 to the 23 atoms in like 20 grams. So it's impossible to, well, now maybe we could look at individual atoms, but 100 years ago, when this was discovered, there was no way to take a look at the individual particles to find out what it was that was moving. So how did they do it? Well, the way they did it was this. There were these two guys called Tolman and Stewart, and what they did was, well, if I have a piece of metal and there's really electrons moving freely, and I accelerate it this way, inertia tells me that electrons should kind of stay, right? Stay back, be pushed to the back, simply because, they're allowed to move freely, so if I'm moving this way, then they're going to move this way. And if this happens, there will be an excess charge here that I can detect. And that's what they did, and they detected the excess charge here, and that's how we know that it's electrons that are moving wires. And remember that that did not make people happy, because all the textbooks were made assuming that it was the positive charges that moved. And still now, we say that current is made of positive charges moving, even though we know that it's negative ones, because we would have to change so much stuff just for that. Last year I told you that positive charges repel with a certain force, so that there's a force between these two guys, but I never told you how much that force was. Well, this year I'm going to tell you how to calculate the force between two charges, and this force is called Coulomb's law, because it was discovered by a guy called Coulomb. And what he did was basically he put a couple of strings and a couple of balls full of electricity, and he looked at what happened when he added more electricity, and he saw that the more electricity that he added, the more these two balls would separate. And from this, he was able to derive his law. So let's take a look at how we could deduce Coulomb's law. Though I can remember that the only valid deduction of a law is experiment. So if it doesn't work experimentally, you can deduce as much as you want. So what does common sense tell us? Well, first thing, we want to find the force, right? So we start with the force. And then we're like, okay, well, he found that the more charge, the more these two things repel. Therefore, the more force, right? So the more charge here, the more force between these two. Okay, so the more charge, the more force, so this has to be multiplying. And of course, the more charge here also, the more force between these two. So this charge also has to be multiplying. Then what he found was that as we add more force, these guys separate, therefore making the force a little smaller. So the idea is that when we make these two charges very far apart, then the force diminishes, and that makes sense, right? Because we don't feel the electric force from galaxies that are really far away. So the more the distance, the less the force. And this distance, I'm going to call it r, and it's the distance between the centers of the charges. And this is very important, not between the surface, but between the two centers of the charges. So we discovered that, okay, the more distance, the less force, so it has to be dividing. But if I just leave an r here and I change the position of this, then this would change sign, and I don't want that. So what I do is I add a square here to make sure that the sign doesn't change. And finally, I need a constant, because the units of this are not the units of nature. So to transform between our units and nature's units, I add a constant called k. Now, it turns out that k is equal to 8.99 times 10 to the 9. And what do you think the units are going to be? Pause the video and tell me. Okay, well, hopefully you paused the video, but I'm pretty sure you didn't figure out the units, so I'm going to walk you through it. First thing we need to find out that, well, we know that the units here have to be newtons, right? So this has to be newtons. And then here we will have the units of k, whatever they are. Okay. Then we need the units of charge, which are, pause the video and tell me. Okay, hopefully you remember that the units of charge are coulombs, because we have two of them, then that's Coulomb squared. And then here we have meters, right? So we have meters squared. So something times Coulomb squared divided by meter squared has to give me a Newton. What can this something be? Well, obviously Newton, so that I can get the Newton here. And then I need to multiply by meter squared so that I get rid of this, and divide by Coulomb squared so that I get rid of that. So Newton meter squared over Coulomb squared. And this is the value for k. Now, some people do not like to express k like this, and they express it in a different way that looks very confusing but actually makes sense. So let me go through it for a second. The way they express k is this. Instead of saying that force equals k times they say force equals 1 over 4 by epsilon 0 over r squared. So this thing here is equal to k. Now, why would anyone do this? Well, the reason they do this is because 4 pi times r squared, that's the surface of a sphere. And if I have this guy doing a force, I can imagine that this force gets spread out over the surface of a sphere that encompasses it, right? So the further that I get, the less force per square meter. So that's why I divide this thing by 4 pi r squared. And then the real electrical constant is this one. And this one is related to the medium where I am. So it turns out that the electric force finds it harder to travel through some mediums than through others. Just like light doesn't travel very well in water, it turns out that the electric force also does not travel very well in water. And that's because both things are related. We'll see later on. Okay? So this thing here, we call it the permittivity, and it depends on where we are calculating the force. Okay? So the permittivity of vacuum is equal to 8.85 times 10 to the minus 12, and the units are just derived from those of k. They're newtons minus 1, coulombs squared, meters minus 2. Okay? And for each material, we will have a different permittivity. And you don't need to know how to calculate this. Whoever's giving you the problem will give you the permittivity of the material. But all that matters is that you understand that the electric force sometimes gets dampened by the material that it's in, and that we can express this by just changing this little constant here. Now, the next concept that we need to look into is that of electric field. And we did this in the IGCSE, but again, we're going to do this in a lot more detail and with a lot more math. So remember that in the IGCSE I told you that here you have this charge, here you have the other charge, and that this guy instantly receives a force. How does this charge know that there is a charge here? And the answer that we gave was that this guy creates this little web around itself that we call the electric field. So that when I place a charge in that electric field, it instantly feels a force due to that electric field. So it's not this guy that's doing the force, it's the electric field around this guy that's doing the force. And that explains how this guy is instantly able to feel that there's a charge here. Now it turns out that we can attach a number to the electric field. And this number will tell us how strong the force will be if I place a guys in here. So I can ask myself, okay, so how am I going to do this? Well, the idea is that I'm not interested in what I put in the electric field. What I want to know is, if I put a charge here, how much force is it going to experience? And the answer is, it depends. Depends on what? Well, it depends on how much charge I put, right? So imagine that 1 Coulomb experiences 2 newtons. Then 2 coulombs is going to experience 4 newtons because there's twice as much charge, and the force is proportional to the charge that I put here. So I can't really tell you how much force you're going to get, but I can tell you how much force per unit charge you're going to get. And that's how we define the electric field. We say that the electric field is the force per unit charge that a charge will experience here. So how do we express this mathematically? Well, easy. First thing, we call it E for electric field. And we say if it's the force per unit charge, then all I need to do, if I have a certain charge here that is experiencing a force, is I take the force that it's experiencing, I divide it by each charge, and then I will know how much force per unit charge is going to experience. And the good news is that I don't really have to do this all the time. I don't have to calculate the force and then divide by the charge. Because if I plug in here Coulomb's law, I can get an expression that will give me the electric field straight away. So let's do that. I have that the force is K, big Q, small q over R squared. And that is divided by small q. So these two q's cancel out. And then I get that the electric field has to be KQ over R squared. So this tells me that if I have a charge Q here, and I want to know how much force per unit charge another charge is going to experience here, then all I need to do is plug in these three numbers, and it will tell me, well, this charge will experience 2 newtons per every coulomb that you put here. What's this thing, we call it the electric field strength, because it tells us how strong the electric field is at a certain position. So let me just write that down. So this is the field strength. And it's very important that you know both this expression, but especially this expression, that the electric field is the force per unit charge. And this goes both ways. Sometimes you will know the electric field, and they'll be like, okay, so if I put a charge here, how much force is it going to experience? Well, the force will be the electric field times the charge. Because this tells me how much force per coulomb. So when I multiply it by the number of coulombs, I will know how much force. Right? So for example, imagine that they say, I have an electric field of 4 newtons per coulomb, and I have a 2 coulomb charge. How much force does it experience? Well, the force will be E times Q, which is 4 times 2 equals 8 newtons. Done. Alright, now it's time to talk about potential difference, and this is one of the most, if not the most important concept in the whole course. So it's very important that you understand this perfectly. If you don't, come to see me, rewatch the video, do whatever you need to do, but you need to understand this very well. Here's the idea. Imagine that I have a charge in an electric field. Now this charge is going to experience a force in the direction of the electric field, because it is a positive charge, right? Because this is going to experience a force, this is going to accelerate and gain kinetic energy. And why is it gaining kinetic energy? Well, it's gaining kinetic energy because this electric field is doing a force over a distance, and that is called work. So the electric field is doing work on the charge, and this work will be equal to the force times the distance that is displaced in the electric field. So it turns out that the electric fields are capable of doing work. Now I can ask myself, what if I don't know how much charge I have here? Can I still talk about the work that this thing does? Well, I can't talk about the work that this thing does, but I can talk about the work that this thing would do if I have a charge here. And again, if I don't know the charge, I can't really say the work, but I could say, well, if I put 2 coulombs, it's going to do 20 joules. And if I put 4, it's going to do 40 joules. So what I can say is how much work per unit of charge this electric field is going to do if I put a charge here and I let it move a certain distance. And that's what potential difference is. The potential difference is the work that this electric field does per unit charge. So let's write this down. Potential difference, and we write that V is equal to the work per unit charge. Now before we get into calculating this, first thing, let's take a look at the units. Well, the units have to be, so the units, remember that this means units, have to be joules, because work is measured in joules and charge is measured in coulombs. So joules per coulomb. Because this is such an important quantity, we just call this a volt. And I know it's confusing because this letter is the same as this one, but this is the quantity potential difference and this is the unit volt. Please do not confuse the two. So potential difference is measured in volts, which is joules per coulomb. So if I know the potential difference between 2 points, I know that if I put a charge in there, it's going to gain these many joules per coulomb. Another thing that's very important to understand is that without the electric field, there would be no potential difference because there would be no force on the charge. So the potential difference needs a field in order to exist. And this goes the other way around. If there's a potential difference, I know that there's a field because there has to be something to be pushing this thing. So if there's a field, there's a potential difference. If there's a potential difference, then there's a field. Now imagine that I want to calculate this for this field. And this field is uniform, means that it's the same all over the place. So what's the force that this charge is going to be experiencing? Well, this force is going to be equal to Q times E, because remember that the field is the force per unit charge. So how much work is this going to do? Well, imagine if this moves a distance d, then the work is just going to be force times distance. So work is going to be force times distance equals Q times E times the distance. Good. So what's going to be the potential difference? Well, the potential difference, remember, is the work per unit charge. So the potential difference V is going to be the work divided by the charge, which is QED divided by Q. This goes, and I get E times D. So in a uniform electric field, the potential difference between these 2 points is the electric field times the distance. If the electric field is not uniform, this doesn't go anymore, because I can't just use this formula for the work. Remember, then in this case, because this is changing, I need to sum all the little increments, and that is equivalent to calculating the area under a certain graph. What is imperative that you understand from this is that potential difference is the work done by an electric field per unit charge, and that is measured in volts, which is a joule per coulomb. Now, because of the definition of volt, we have another unit of energy that's very used when we're doing particle physics, when we're considering very, very small things. And the idea is this. Imagine that I have a potential difference from here to here of 1 volt. And here I have an electron. So this is 1 electron that has charge 1.6 times 10 to the minus 19 coulombs. So imagine how big the coulomb is when the charge of an electron is 10 to the minus 19 coulombs. It's huge. You have billions of electrons in 1 coulomb. Okay, so I have this electron here, and it goes through a potential difference of 1 volt. How much energy does it gain? Well, the energy will be equal to, as always, the energy that it gains is the work done by the field, which is going to be the charge of the electron times the potential difference. So in this case, it's 1.6 times 10 to the minus 19 coulombs times 1 volt. Okay, so 1 volt. So this will be equal to 1.6 times 10 to the minus 19 joules. Okay. Well, this thing that we just did is called an electron volt. That is, this is the energy that 1 electron gains when going through 1 volt of potential difference. Therefore, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And this is the way that we measure energy for particles in things like the LHC, the Large Hadron Collider that's now in Switzerland, where we are taking photons or protons or electrons and things like that, and we're accelerating them across this circuit that is kilometers long, and the energy that we're giving these protons or electrons is measured in electron volts, normally in giga-electron volts, because it's such a huge energy. The last thing that we need to revisit is the notion of electric current. And from the IGCSE, hopefully you remember that the idea of electric current is I have a wire where there's electrons that are moving with a certain speed, and here I am, and I make this little wall in my wire, and I start counting how many coulombs of charge go through this piece of wire, through this wall. If I measure how many go through this wall every second, that is the electric current. that is the number of coulombs that go through where I'm standing each second. So we can write it like this. We call it I, and I stands for intensity because that's how it used to be called and how we call it in more technical terms. So the current will be equal to the amount of charge that crossed this, which I'm going to call change in Q, because it's the change in Q that went through here, and divided by the time that it took them to go through, which is change in T. So basically, if I want to know how much charge went through here, I take all the charge that went through here in, let's say, 4 seconds, then I divide by 4, and then I know how much charge went through here in a second. Now this is the easy part, and that's what we did in the IGCSE. The next thing that we would like to do is to relate this to the two things. First thing, the average speed of the electrons, which we're going to call the drift speed. So these electrons, we can imagine like they're actually moving really fast in all directions, but on average, they are moving this way, all of them. So they're just moving around, and on average, they keep advancing slowly to the right. Okay? So we call this the drift speed, and it's the average speed of the electrons going this way. And I'm going to call this drift speed V, small v. Now the next thing that I'm interested in is the amount of electrons per unit of volume. So how many electrons per meter cube do I have in this wire? And I'm going to call this thing little n, which is like a density of electrons, right? Amount of electrons per cubic meter. And now what I'm interested in is, can I derive the intensity in terms of this drift speed and this amount of electrons per cubic meter? And the answer is, of course, I can. And in order to do so, what I need to do is to find the amount of charge that goes through here in a certain amount of time increment of t. Okay, so imagine that I'm here and I start my timer and I wait a certain time increment of t. Now, the electrons that were here will have moved then, right? A certain distance will be the speed of the electrons, v, times the time that it took them to move, which is the increment of t. So these guys here will have moved a distance, v, increment of t. Great. Now, how many electrons have gone through my wall? Well, all the ones that were here, 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 until here, right? So all of this volume of electrons will have gone through my wall. So what I want to calculate now is the volume of electrons here. Now we know that volume is equal to the area times the height, right? So in this case, the area is just A, which is the area of my wire, and then this height, or the length in this case, is V times increment of t. So the total volume, that's big V, is equal to area times V times the increment in time. So how many electrons went through here? Well, since this is the number of electrons per unit of volume, the total number of electrons that went through will be NV. And how much charge went through here? Well, if this is the number of electrons that went through, and we know the charge of one electron, and we call it Q, then the total charge that went through here is Q times the number of electrons, which is Q and V, where V is the volume of this thing. So now what I'm going to do is I'm going to put it all together and make a formula for the drift, for the current in terms of the drift velocity and the density of electrons. So there you go. First thing, how much charge went through here? Well, as I said, the charge will be this, which is equal to this, which is equal to this. So Q and V, but this volume here is just this thing here, right? So this is equal to Q N A V increment on t. Good. And now all I need to do is to plug this into my equation at the beginning. So then the current will be equal to Q N A V increment of t divided by increment of t. And because I have two increments of t, they cross out. So that I have Q N A V. And this is the equation that gives me the current in terms of the number of electrons per cubic meter, the area of the wire, the drift speed, and the charge of the electron. What if I have some material where it's not the electrons that are carrying the electricity, but some other charger, like for example protons? Well, all I need to do is change the charge here, and then that will give me the drift speed of the charges in that material. Alright, we're finally done, so now it's time to take a look at the learning objectives and see whether we fulfill them. So first thing, identify two forms of charge and the direction of the forces between them. We knew this from the IGCSE. Solve problems involving electric fields and Coulomb's law. Well, hopefully you can do this now that you know this. Calculate work done in an electric field in both joules and electron volts. We just did that when we introduced potential. Identify sign and nature of charge carriers in metal. We know that it's electrons and that the charge is negative. Identify drift speed of charge carriers. Well, you can do this now thanks to the equation that relates current and drift velocity. Solve problems using the drift speed equation. We're going to do this in class. And finally, solve problems involving current, potential difference, and charge, which is what we're going to do in class. Alright, so sorry for the long video again. This is quite difficult. It's going to get harder, but I think that once you start doing the problems, you'll soon get the hang of it. I'll see you in class. Bye.